Before going into bootstrapping, I'd like to quickly summarize what we did on Wednesday. I already have another video that summarizes what we did on Wednesday, so this is just like a 1 minute summary to take us to where we stopped and we can make progress from there. So it's an hypothetical poll between Ed Orgeron and Nick Saban. We have 1,000 votes within the poll, and it indicates Nick Saban has a winning chance of 51.1%. And the question is whether this was conclusive by itself. And we will evaluate the confidence in this conclusion. So we used computer simulation as discussed last class, and we were able to generate 1,000 different estimates of Nick Saban's winning chance. And we plotted up that in a histogram and moved on to introduce the concept of confidence interval, 95% confidence interval. And it's all about the area of this histogram between the 2.5th percentile and the 97.5th percentile divided by the total area. So this area between this interval and the total area of the histogram will be 95%. And we get that by looking for 2.5th percentile here and 97.5th percentile here. So there will be 2.5% of the data outside of this vertical line, 2.5 outside of the left vertical line, so that you can sum up those two and you have 5%. Everything else is the 95%. So there is 95% chance that the true winning percent of Nick Saban will lie within this interval. And what is this interval? Is the interval between 48% right here and 54%. The midpoint will be the 50th percentile, and it generally tends towards the true or original sample mean, which was 51.1. So from the sample which contained 1,000 votes, we are able to make the conclusion that there is 95% chance or probability that Nick Saban's true winning chance will lie between 48% and 54. If his winning chance is 48%, does he actually win? No, he loses at 48%. 50 is the cutoff. So this result is inconclusive because he could either lose when it's lower than 50 or win when it's above 50. And the question is, how do we possibly determine the number of samples we need to arrive at a conclusive result? And we can actually find that out by performing more computer simulation. So the previous computer simulation was for 1,000 votes, and that was right here. So we can do computer simulation for 10,000 instead and see what the range in the winning percentage will be. And that's the focus in the next section. So we create a function called sampling distribution, takes in a win percentage. By default is 1,000, but we can change this, and this is actually what we will change to generate several more samples. So this will be equal to the number of realizations we want, but this is the number of votes in each realization. So we're going to keep that at 1,000, just like the original poll, but we ask for more realizations. We can do 10,000 or more. So that's the function there. We have another function called quantiles, and this basically gives us the result we were able to obtain graphically here. So you don't have to plot this graph to obtain this interval. you can just use this quantile function which we provide. And it basically calls this function with any given number of samples. It creates a data frame similar to this. Then we're going to grab the quantile using the quantile function from a data frame. So the quantile function from a data frame, which is coming from pandas, is different from the quantiles function we defined, right? This is def, so this is our function. It's called user defined functions. This is defined by those who programmed pandas. So it's going to give you the data at 2.5 percentile and also give you the data at 97.5 percentile. So by just calling this quantile function with any winning percentage, true winning percentage, you get the interval, which is precisely the same interval we got visually here. So just another way to get the same thing, but we're going to use these functions in the next section very shortly. So again, we're summarizing the result that there is 95% confidence that your data will lie in this interval. So now we move on to figure out how many realizations of this poll do we need to arrive at a conclusive result. So instead of 1,000, let's just try 10,000 and see what the range will be. So we use the function we just created, provide a winning percent of 50. This is just for testing, so not necessarily the same as 51.1, but we're asking for 10,000 samples. So all of that is generated and stored here, and we plot the quantiles just like we did before and look at the 95% confidence interval. Interestingly, it goes from, we went in with 50%, right? So it's still at the mid is centered at 50, meaning the 50th percentile is right here in the middle. And that's the point estimate, by the way. And what is the margin of error? Plus or minus 1%, right? 50% minus 49% is minus 1. And on the right hand side, which is the plus 1, 51 minus 50 plus 1. And when you call the quantiles function we created, it gives you those two values, which is 49 and 50. That's the confidence interval. And you can summarize that result here again. This is how you will be summarizing the results in your lab workbook 8. You provide the point estimate, which is the mid or the data at the 50th quantile, it's shown here. That's the point estimate, and the margin of error is plus or minus the value at 2.5 percentile and the value at 97.5 percentile. So the margin of error is within 1% if you use 10,000. If you had used 1,000 like we did before, what was the margin of error? 3%. 51% minus 48, 3. 54 minus 51, 3%. So what we're going to do next is to use a larger sample. So we actually have another poll, which is poll-larger.csv. So we want to try out a poll with 10,000 votes and see if the results from that poll will be conclusive by doing exactly the same kind of study we did here. So repeat the process, and that is actually what your lab workbook will be. So just looking at the data, we haven't done any computer simulation here. The computer simulation is what you will do in the lab. So we're loading the data just like we did before. Calculate the sample winning chances. It's 51.8 now when you pull 10,000. So when you pull 10,000, it's indicating that Dodgeron will win. When we pulled 1,000, it indicated um, Nick Saban will win the election. So that's what you get from sampling variability. Your sample may not be representative of the population, which is why we are learning about how to use computer simulation and data bootstrapping to evaluate the confidence in the results you obtain from any sample size, which may not be representative of the entire population. So this is the question you're going to have to answer in the lab workbook. Is explained there. Give me the 95% confidence interval, the point estimate, and the margin of error. And like I said earlier, it's just going through this process we did for 1,000, but now you're using 10,000 samples. It's important to know what value to modify. Are you modifying this to be 10,000, or are you modifying this? Obviously, you shouldn't modify both of them. This is the number of votes in each of the realizations. So you want to keep this at 1,000. This is the number of samples. So this is what becomes 10,000. And I should warn you, this might take a while. So when it's running, you might see a star here. It doesn't mean it's crashed yet. It just means it's still running. In general, it shouldn't run too long. If it's running too long, maybe you can reduce this, but don't reduce this, right? This is the 10,000. This you can reduce a bit to 500 and let it run, get the results quickly. And when it works fast enough, you can do the 1,000 and 1,000 on this, 10,000 on this, and just let it run to completion. If your notebook actually crashes, it still shows at a star and is running for like 5 hours. Yeah, it probably crashed already. And in that case, you have to close out all your workbooks, close out Anaconda, and restart the file. But first off, you have to save so you don't lose your work. So anytime it crashes and you see a star next to what you already ran and it's taking much longer than usual, save first, then close it out. Close out Anaconda, close out by Jupyter Notebook, then open it up again, and you'll be back in business. Okay, so that's what you're going to be required to do in Lab 8. And now we move on to bootstrapping, which is a very important concept. All it is sampling with replacement. And I'm going to illustrate it very quickly using Excel. So, assume you have an array X and it contains random numbers between 1 and 6. So, but let's assume there is no number repeated. So this is an array X. It's 1, 2, 3, 4, 5, 6. And we want to create multiple, we want to sample from this and create an array of the same length, meaning it has 6 entries too. And it's sampling with replacement. So it's possible you select, say, 4, then randomly choose any points here, 5, randomly select any points, 1, randomly select any point, 6, randomly select any point. Let's assume it gives us 1 again, which is why it's sampling with replacement. Some values could be repeated. Choose any number randomly, 4 again, that's fine. Sampling with replacement. If you sample without replacement, All your values will be 1, 2, 3, 4, 5, 6, but you're just changing the order. So we can generate more samples. And an easy way to sample with replacement here for this problem is to choose random numbers between 1 and 6, right? That's precisely what these numbers are. So the order can be anything. So you see, this is another realization. And every time you copy and paste, the number changes. And we can actually do that for all of this. So now, this is the kind of result you get from bootstrapping. We've created 10 samples with replacement from this sample. And you can calculate the mean of each of these, which is what we do in bootstrapping. You'll see that when I turn back, I should have increased this size a bit. And these are the means of each of the bootstrapped samples. So these right here, the x1 through x10, these are the bootstrapped samples. These are the bootstrap samples. This is one bootstrap sample. This is another bootstrap sample. And when I'm talking about the bootstrap mean, is these guys, the mean of each of those samples. And you see it's different from the mean of the original sample. The mean of the original sample is 3.5. So when you sample with replacement, the mean could be anything. So the mean is changing. And these are the means we grab and then do a histogram on. So with that, I'll turn back to this spreadsheet, this notebook. And we're going to be looking at midterm part 1 results from last semester. The 36 students were in the class. You don't see who got what score, but you can see the average. So if I run this data is also already provided on your GitHub page for this course. You get the head, 28, 48 is this number between 0 and 50, right? 50 is the highest score you can get on part 1 of the midterm. So these are some of the grades, the first 5. Histogram of the grades. It looks weird, right? And this is not symmetric, so it's not like a normal distribution. If you get the mean of these, would you think that would be the mean if all students in LSU took this course? Maybe not. That's what we're trying to find out. Is this sample of 36 representative of an average second year student at LSU? Before we get into that, here I'm just describing the grade, so use the describe function.